Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Jr., your math tutor and an instructor of mathematics at the University of Liberia. So in my today's lecture, I will be looking at differential equations, and particularly I'll be looking at variable separable type 2. So in the first step, we discussed that if you have a differential equation, you can easily separate the variables on both sides of the equations and integrate both sides to get your general solution. In type 2, we looked at problems wherein we cannot just separate the variables. We must first bring in some substitution before we end up at variable separable. That's why we call type 2 reducible to variable separable. So let's get started. So there's an additional problem we want to solve. We solved several other problems initially, so you can just check the other videos and maybe you can practice more. So in this problem, we have dy by dx equals to sine of x plus y plus cos of x plus y. So we have the same angles right here. We can just say, let a variable be this, and that same variable be this. So we can use u, let u equals to x plus y. So u is a new function, y is the initial function. So we must differentiate u with respect to x. So the derivative of x is just 1 because it's an independent variable. We must differentiate y with respect to x. So we have dy over dx. What do we do next? We solve for dy by dx. Send this one across. You have du all over dx minus 1 dy all over dx. So this is the first step. We now substitute. So this is du over dx minus 1. This is dy by dx equals sine of x plus y now is u, cos of u. So if we multiply all side by dx, we have du minus dx equals sine of u plus cos of u dx. So if we just separate the variables, we will have dx plus sine of u plus cos of u dx. So dx and dx, we can factor out dx. So we have the u equals dx. Dx into dx is just 1 plus sine of u cos of u dx. Now we want only x, since these are in u, so we must get rid of it. Also, we divide on this side. So we have 1 plus sine of u plus cos of u. So this will cancel this one. You have the u now all over 1 plus sine of u plus cos of u must be equals to dx. So the variables have been separated. We can now integrate both sides to find the general solution. Now, on the right hand side of this integral of this equation, the right hand side is very easy to integrate. The left hand side has the issues. So we know that 1 is equals to cos square. Now, since we did it with u, we say cos square u plus sine square u. That's what we know, right? What if we divide all angles by 2? We will have cos square u over 2 plus sine square u over 2. So we're going to use this identity to replace 1. The next one we want to replace is sine of u. We know that sine of 2u is equal to 2 from the double angle, u cos of u. We divide all angle by 2. We will have sine of u to be 2 sine of u over 2 cos of u over 2. So where's where we see sine of u We're going to replace it with this. Lastly, cos of 2u equals cos square u minus sin square u. So if we divide all sides by 2, all angles by 2, not side but all angles, we will have cos of u equals cos square u over 2 minus sin square u over 2. So we want to use these three trigonometric identities in this integral. So we have the integral of du. This 1 is cos square 1 over 2 plus sin square 1 over 2. Oh, not 1, but u over 2. Move to the next one. Plus sine of u is this one. So we have 2 sine of u over 2 cos of u over 2. Plus, last one, we have cos square u over 2 minus sine square u over 2. All equals, now the integral of the x is just x. So what do we observe? We observe that the second term and the last term can go out. And then the first, the second to the last can be added. So we do have the integral of the u or over 2 cos square u over 2 plus 2 sine of u over 2 cos of u over 2 or equals to x. Now what we also know is that we know that the integral of secant square u over 2 is equals, or let's say the general form, right? The integral of secant square u du is just equals to tangent of u. Now, if we divide every term, that is, here we say 1 all over cos square u over 2, and then down here we say cos square u over 2. This side we say cos square u over 2. It's just like, it's just the same because this guy is, this numerator is 1 over cos square u over 2 divide. Now this is kind of like saying there's a coefficient of 1, for example, divided by this. So it's like saying 1 all over cos square u over 2. So if you reciprocate, this u over 2 and this u over 2 will cancel. This cos square u over 2, cos square u over 2 will cancel. So it's just like rewriting the problem. So we did not change anything in the problem. So don't panic that we brought something new. What we're trying to do is to be able to easily integrate this integral. That's just all. So this can result to the integral of secant square u over 2 divided by, this one is just 2, plus, or we can factor out 2 from here, and so it just be 1 over 2. 2 and 2, we just factor it out. So this will just be 1. Plus, now sine, this is sine u over 2, sine u over 2 times cos u over 2 divided by cos u over 2 cos u over 2. So this cos u over 2 can cancel this cos u over 2. So we'll be left with sine over cos, which is just tangent. So down here is tangent u over 2. All equals to x. So I'm taking my own time so that you have a basic understanding of what I'm doing. Please, if you have any concern at any time, in the comment section, put your concerns there, and I will immediately get to you. So we have 1 over 2. the integral of secant square u over 2 over 1 plus tangent u over 2 to u equals to x. Now we can bring in u substitution. Whenever u is this the denominator, we will know that the derivative of tangent is equal to secant square u. So we can say now we already used u initially, so let's say let t equals to 1 plus tangent u over 2. So the t now would just be secant square u over 2 times the derivative of u over 2, which is just 1 over 2 du. So this time, this, it just comes right here, this 2. So you just have the du. Now, wheresoever we see this numerator, we're going to put 2 dt. So we have 1 over 2, 2 dt, all over u. So 2 and 2 cancel. This is x. So we will now have the integral of dt over u is just the ln of u. Is it dt over u or dt over t? This is t, not u. It's just the ln of t. Equals to x plus some arbitrary constant c. So at this point in time now, we bring in the value for t and bring in the value for u. So t is 1 plus tangent u over 2. That is t. X plus c. The ln of 1 plus. So what is u? U is x plus y all over 2 is our u, or equals to x plus c. So you can stop here. Somebody can say, I will stop here. But another person could say, no, I'm not going to stop there. I want to simplify that expression further. Just to simplify it a bit, just small, just a bit, So I know that if I say e raised to ln of 1 plus tangent of x plus y all over 2, I'm going to get what is in here. Equals, I do the same on this side, e raised to the power x plus c. So e raised to this is just equals to what is here, the argument, which is 1 plus tangent of x plus y over 2 equals e raised to x times e raised to c. So this e raised to c is a constant. So we will just represent it with some constant. We can call it a or b. So if you let you send this one across, it doesn't matter. We have tangent of x plus y over 2 equals, so since this is a now, it's just a e raised to the power x minus 1. So you see it has been reduced in a more compact form than this. So thanks ever so much for watching. Please subscribe and see you in our next lecture. Thank you.